Today's video is about LOLOL diagrams and problem solving using energy concepts in physics. Let's say that on a test you get a problem similar to this one. A 4-kilogram ball begins to roll down a hill 15 meters tall. Its height over time is shown in the graph above. Assuming no energy is lost to friction, what is the ball's velocity at points B, C, and D? Now, in most of the problems we've dealt with so far, we've only had to do one situation. For example, if a ball is dropped from a specific height, say h, what is its velocity when it hits the ground? But in this situation, we're not doing just from point A to point D. We have to figure out the speed of the ball at points B and C as well. In order to do this, we are going to use a specific tool called LOLOL diagrams. LOLOL diagrams are basically the same thing as LOL diagrams, except that instead of showing two snapshots in time, like an LOL diagram, you can actually show 3 or more snapshots in time and change the system that's acting in each little bit. The best way to understand how an LOLOL diagram works is to see it in action. So why don't we go back to number 1 and look at how we could apply this new knowledge to that problem. The simplest place to start in this problem would be to find the energy of our Earth ball system at the beginning before it starts rolling down the hill. So let's go from point A, which is at the top of the hill, to point B, which is some height lower. It looks about to be half the height of the hill at the beginning. And be careful, this graph is not meant to be a picture of the hill it is rolling down, it's merely the ball's height over time. So, at point A, our ball is 15 meters in the air, which means that it has a gravitational potential energy of 15 times the mass of the ball, which is 4 kilograms, times the gravitational field strength of the Earth, which we're going to say is 10 newtons per kilogram. So potential energy gravity is equal to 10 times 15 times 4, which is equal to 600 joules. So we're going to put that in right here. 600 joules. Because the ball isn't moving at this point in time, it's resting on top of the hill and is about to start rolling down, we have no kinetic energy. We said that there is no energy lost to friction, so there's no internal potential energy, and there's no spring acting in this situation, so there's no elastic energy. And I should have defined this earlier, but our system is the ball-earth system. Now, at point B, we can see that our height is a lot less than it was when we started off at point A. It looks to be about 7 or 8 meters. Let's just call it 8 for right now. And obviously, because it started rolling down the hill, it has some kinetic energy, and we'll find out what that is in a second. So let's go back to our LOL diagram. We said it was about 8 meters, so potential energy of gravity is going to be equal to the strength of our gravitational force, which is 10 newtons per kilogram, times the mass of the object, which is 4 kilograms, times our height off the ground, which is 8 meters. So our potential energy of gravity is equal to 320 joules. And we're going to put that in right here, and we're going to make our column about half the height of the initial potential energy of gravity because it's a lot less, and this is going to help us visualize the situation better. So we have 320 joules of potential energy of gravity. As we said earlier, no energy is lost to friction, so we have no potential energy internal, and there are no springs, so we have no elastic potential energy. So, because no outside force is doing work on the ball-earth system, we know that all of the missing potential energy of gravity that isn't in right here has to be in the kinetic energy. So, obviously, 600 joules minus 320 joules is equal to 280 joules. And we'll draw that in right here. So our kinetic energy is 280 joules. But that's not what the question is asking us. The question is asking us, what is the ball's velocity at point B? So we know that our kinetic energy is equal to 1/2 mv squared. If our kinetic energy is 280 joules, and our mass is 4 kilograms, we can solve this and we find out that 140 is equal to our velocity squared, and so our velocity is equal to about 11.8 meters per second at point B. And you'll notice how I've labeled each of these L's as point A and point B. This is going to come in handy later on for identifying what is what. The next thing we need to find is the ball's velocity at point C. So let's make an LOL diagram going from point B to point C. So I'm going to draw out my L, O, L, and I'm going to erase all of this so that we can have room to make another L later. And ideally, I would have enough space to do my LOLOL all in a big line, but my handwriting is too big and I'm sad. I'm sorry. So I'm going to label my axes first. I'm going to write kinetic energy, potential, it's supposed to be an E, potential energy of gravity, potential energy internal, potential energy elastic. Then we have kinetic energy, potential energy of gravity, potential energy internal, and potential energy elastic. And our system in this problem is the same as it was previously. It's still the ball earth system. And I'm going to label my L's as point B and point C. And I'm going to recopy what we had for point B earlier because nothing has changed there. 280 joules, 320 joules, and so now we are ready to go on to point C. At point C, our height looks to be about 10 meters, which means that our gravitational potential energy has increased from point B, but it's still less than it was at point A, which means that our kinetic energy must be less than it was at point B if our energy is conserved, but we can see that more clearly on our LOLOL diagram. So, as we said, potential energy of gravity is equal to the gravitational field strength, 10, times the mass of the object, times the height of the object at the specific time, which means that our potential energy of gravity is 400 joules. And we'll write that in right here. And that's taller than it was earlier. So 400 joules. We still have no friction, so we don't have any internal potential energy, and we don't have any springs, so we don't have any elastic potential energy. So in order to conserve our 600 joules of energy, which we can also see up here at point A, that is going to be equal to our kinetic energy plus our potential energy of gravity. So 600 joules minus 400 joules is equal to 200 joules as our kinetic energy. So that's going to be half the height of the potential energy of gravity. And now that we know our kinetic energy, we can again solve for our velocity. So our kinetic energy, 1/2 mv squared, like we said earlier, 200 joules is equal to 1/2 times 4 times v squared. So 100 is equal to v squared. So 10 meters per second is our velocity. Remember, our velocity earlier at point B was 11.8 meters per second, and we now have our ball going 10 meters per second at point C. So I'm going to erase that. And now we are going to move on to probably the easiest part of this problem, which is point D. Point D is at the very bottom of the hill, so we can see that we have no gravitational potential energy, which means all of our potential energy from point A is going to be turned into kinetic energy at point D. However, we should probably graphically represent this as in our LOL diagram. So we have our L and our O and our L. This is going to be point D. Our system hasn't changed because nothing outside is acting on the system, so it's the ball, earth, system. We have kinetic energy, potential energy, gravity, potential energy internal, and potential energy elastic. We still have no friction, so we have no internal potential energy. We have no spring, so we have no elastic potential energy. We said that at point D, we have no potential energy of gravity because it's at no height off the ground, which means that all of this energy must have been translated into kinetic energy. And as we can see at the beginning, we had 600 joules of potential energy of gravity that were translated into kinetic energy at the very end. So 600 joules of kinetic energy. And just as we did the previous two times, kinetic energy is 1/2 mv v squared. 600 is equal to 1/2 times 4 v squared. 300 is equal to v squared. So our velocity at point D is equal to about 17.32 meters per second. So here are our three velocities for the 3 points that the question was asking us for. Let's do one last problem involving LOLOL diagrams. A 6 kilogram skateboard is traveling 8 meters per second when a 10 kilogram brick is dropped onto it from 2 meters in the air. Then another 10 kilogram brick is dropped from 3 meters in the air onto the brick skateboard system. How fast is the skateboard traveling after the first and second bricks, assuming no energy is lost to heat or vibrations? And to give you a little visual for what is going on in this problem, we have a skateboard traveling at 8 meters per second when a brick, this is a little bit later, a brick is dropped onto the skateboard, and then later on we have a brick being dropped onto that brick on the skateboard. So let's go ahead and do our LOL diagrams. I've already drawn out the LOL diagrams for this in order to save some time because the process can be a bit tedious. Let's go ahead and fill in what we know. It says in the problem that no energy is lost to heat or vibrations in this entire problem, regardless of what system we're using. So let's go ahead and cross off all of our internal potential energies in this situation. In our first situation, we are going to be dropping the brick onto the skateboard. So we're going to be analyzing the brick, skateboard, earth system. The skateboard is rolling along the ground, so it has no potential energy of gravity. But the brick does because it's being suspended 2 meters in the air. So the potential energy of the brick is equal to the mass of the brick, which is 10 kilograms, so potential energy, gravity, is equal to 10 kilograms times the strength of the gravitational force, which is 10 newtons per kilogram, times the height at which it's dropped, which is 2 meters. So our potential energy of gravity for the brick earth system and in the entire brick skateboard earth system is going to be 200 joules. So let's draw that in real quick. At the moment before it's dropped, the brick has no kinetic energy because it's still being suspended, but the skateboard does. So this kinetic energy of the skateboard, which I'll try and fit in here somewhere, kinetic energy of the skateboard is equal to 1/2 times the mass of the skateboard, which is 6 kilograms, times 6, times the velocity of which is traveling squared, which is 8 meters per second squared. So our kinetic energy for the skateboard is equal to 192 joules. So let's draw that in right here. Slightly less. 192 joules. We know that there is no elastic potential energy in this situation because there are no springs that we're dealing with. And we're going to go ahead and mark off the elastic potential energy in these situations as well because we're not going to be adding anything else that involves a spring later on. We're only going to be adding in the brick. So our total energy of this brick skateboard earth system is going to be 392 joules. Let's look at what happens after we drop the brick. After we drop the brick, we have our brick lying on top of our skateboard, and they are both traveling at the same speed, which means that we have no potential energy of gravity because they're both lying on the ground, and we can treat them as one object because we're treating them as a system. And all of this potential energy of gravity has been translated into kinetic energy. So we have 392 joules of kinetic energy after the first brick is going. So the first problem is asking us, the problem is asking us what the velocity of the skateboard is after the first brick and the second brick. So after the first brick, our kinetic energy is equal to 392 joules. And we know that our mass is actually equal to that of the brick and the skateboard because that is our new system, quote unquote, that's traveling. So our kinetic energy of 392 joules is equal to 1/2 times the mass of the brick plus the skateboard, which is 6 plus 10, which is 16 kilograms, times the velocity squared. So 49 is equal to our velocity squared. So 7 meters per second is our velocity after the first brick is dropped. Now we need to find out the velocity of the skateboard after the second brick is dropped. However, because we have this new brick, we need to include that in our system. So our new system is actually going to be the brick skateboard, and I'm using that to denote that they're sort of being treated as the same object right now. The hyphen. Skateboard. Earth. Brick system. So, because our brick is in the same position that the first brick was, in that it is not moving until it's dropped, and we're looking at it before it's being dropped, it actually has potential energy, but no kinetic energy. But our skateboard and brick are still moving, which means that they have kinetic energy. So let's take that kinetic energy from after the first brick. Because no other forces have acted on this system, they're still moving at the same velocity. So we have 392 joules of kinetic energy in that brick skateboard object. And our potential energy of gravity between the brick and the earth is going to be equal to the mass of the brick, which is 10 kilograms, times the strength of the gravitational field, which is 10 newtons per kilogram. And we also have a height of 3 meters on this brick. So our potential energy of gravity is going to be equal to 300 joules. So right about here is going to be our potential energy of gravity. Once the brick is dropped, it's going to have no potential energy of gravity because it cannot go down any further because it's going to become part of that brick skateboard object, so we're going to have a brick skateboard object. And all of this energy is going to become consolidated into kinetic energy. So we know that, and because our total energy is equal to the potential energy plus the kinetic energy, and our total energy is becoming the kinetic energy, we can say that our kinetic energy now is equal to 692 joules. And we need to find the velocity, but we have our kinetic energy now, so that's pretty easy. We have kinetic energy equals 1/2 mv squared, like above. Our kinetic energy is 692 joules. And our mass is now not only the brick skateboard mass, but it's the brick skateboard brick mass, which means we need to add the weight of the brick, which is 10 kilograms, to the weight of our brick skateboard object, which is 16 kilograms. So we're going to say that this is a 26 kilogram object moving at a specific velocity. So 53.2 is equal to our velocity squared. And our velocity is about equal to 7.3 meters per second. You could have solved this problem using momentum if it had been given to you on a test, but it's good to see an alternate way of solving these physics problems to know that they all kind of tie together. I hope you found this video to be informative, even though it was slightly long. I hope I didn't annoy you too much. Have a good day.